side. So what's our thinking on this problem here? We have this piecewise function. We want to know the limit of the function as x approaches 1. And what I'm mostly interested in is how are you going to approach this and show your work? And it really goes together. The way you show your work on this, showing work in calculus is important for more than just that old, thing we always do in math, because the work that you do really is guided by and guides your thinking process. And as we get further and further into calculus, the process gets more complex. And so you really do need to be working stuff out as you go along, and you got to be able to go back and troll through your work if you get something wrong and try to figure out where you made a mistake. I can't tell you how many times in college, not so much in my math classes, but in my physics classes, where the math was honestly harder than my math classes, going through a huge problem set. Like I had a quantum mechanics problem set one time where 4 problems, and it ended up being over 100 pages of work. I mean, it was just a brutal problem set. And I was working with a group, and we kept getting this one wrong, but it really helped. Eventually, we were able to go back through the work. And because the work was written out pretty carefully, once you found out where there's a little error, it was pretty easy to fix it and get to the right answer, right? But I mean, math gets, this is tough stuff. I mean, you're going to do a lot of math this year, but the further you go, the more expansive it becomes, and the more important it is to keep track of what you're doing. That extends into coding too. Like when you're coding, it's real similar to math. I mean, you have to document your coding really well so that you're able to debug it and figure out where things went south on you, right? Okay, enough said about that. Let's focus on this problem. How are we going to do this? Ideas. What must be true for the limit of this function to exist as x approaches 1? That's exactly it. That's how we have to approach this, right? We have to approach this as two one-sided limits and show that they exist and agree. And if they do, then that's our limit, right? So we would take this, we would say the limit of f of x as x approaches 1 from the left would be the limit of what expression? Top one, good. So this is the part of the function that we're dealing with when we're approaching 1 from the left. Okay, make sense? So we're taking the limit of the expression 3x minus 1 as x approaches 1 from the left. And what is the answer? What is that limit? 2. Yeah. Okay. The limit of f of x as x approaches 1 from the right is the limit of what expression then? 2x. Yeah, this would be the part of the function an ant is walking on when approaching x equals 1 from the right. Whoops. And if I approach 2x as x approaches 1 from the right, and does the direction even matter here? No, we're still just plugging in 1, aren't we, when we directly evaluate, and we get 2. Okay, well, look at that. Those two are equal. So what's the answer? It's 2. Yeah. Okay, does it matter that the actual value of the function at x equals 1 is 4? Makes no difference, right? Makes no difference because the limit, again, is unconcerned with the actual value of the function. All it's concerned with is the value that we're approaching. Remember, it's the values that ants from the left and the right would anticipate stepping on when they got to 1, not where they actually end up, where they think they're going to be as they get infinitely close. Okay, give me thumbs on that. Is that making sense? All right, good. Okay, so we're not going to deal with the third case here. We're just going to look at these first two cases. These are two special trig limits that we're just going to use. And man, I really miss proven number 1 because it's such a cool proof. But again, I'm going to resist the temptation to do that one. And I'll let you watch that one on AP Central or AP Classroom. Uh, these are both true though, but they are both indeterminate, right? If I were to try to evaluate limit number one directly, I would get 0 over 0, indeterminate. But they're telling us that that indeterminate limit is actually equal to 1 when you do the math. If you analyze that one, if you evaluate that one analytically, you get 1. Okay, but we're just going to take that on faith for now. We could show it graphically. I mean, actually, let's do that real quick. If I pull up the function f of x equals sine x divided by x, and if I focus in close to x equals 0, well, pretty clearly, what value is that function approaching? It's approaching 1, isn't it? Now, if I drag my cursor along, when I actually get to 0, if I can, yeah, it's undefined, right? There's a hole there. But every place, so that's really cool how Desmos does that now. It even gives me a, look at that, it even gives me a open circle there, right? That's pretty amazing it does that. Did not used to do that. But we can see that that limit is 1 visually, okay? And we could even show the other one, 1 minus cosine x over x is 0. Yeah, okay, if we look at this one, as x approaches 0, it's undefined, right? But pretty clearly it's approaching y equals 0. So we get those two special limits that we can rely on. Those are ones you just kind of have to memorize. And I keep saying this, but I need to get organized and give you guys a list of things to memorize. It's about time for a memorization quiz here, just so you have this stuff available to you, because it needs to be in your working memory, part of your working tool belt of knowledge, so you don't have to pause and break your train of thought to think about this stuff. There's just some really key, uh, you know, binomial expansions, a couple of those, a couple factoring patterns that'll go back from the previous 2 years, some trig stuff you got to remember. We need to take a day on the unit circle here at some point pretty quick. But those are ones you're just going to remember. Okay, what about this first one? Let's try this. The limit of tangent x over x as x approaches 0. If I evaluate that directly, what do I get? What's tangent of 0, by the way? Nobody remembers tangent. I don't either. Nobody really remembers what tangent values are. But what do you always break tangent up into? It's you take the composite trig functions, tangent, cotangent, secant, cosecant, and you always think of them in terms of what? Sine and cosine, because we do know those, right? So so it's 0 then, isn't it, right? Tangent x is sine x over cosine x, so that's giving me 0 over 1, right? 0. Okay, so it is 0 over 0, right? That's indeterminate. What's that mean? Just like before, it means more work. But this time, the more work amounts to manipulating this expression, the argument of the limit, the stuff inside the limit. I have to manipulate that so I can extract one of my two available known trig limits. Yes, sir. Identities? Oh, yeah. Trig identities always work. Yeah. Yeah. Identities are things that work regardless of the input value. Those are fair game all the time. Okay. So, what trig relationship? I mean, we don't know anything about tangent x. That is not a known indeterminate form for us. We only have two. So, any ideas what I could do with this? What do you think? Well, for one thing, both of our known special limits involve sine and cosine, right? So what's the first thing we probably should do here? Write tangent in terms of sine and cosine. Okay, so this would look like then the limit of sine x over cosine x. Does everybody agree with that? I maybe skipped a step there, but does everybody agree with that statement? Okay. Now what? I'll give you a hint. There's a property of limits that we want to use here, and I think I'm going to just copy and paste so I don't have to write so much. I think I've got it coming up here. No, where the heck is it? Right there. What the heck? How do I? Oh, there it is. Okay. Okay, we've got that property of limits. What's that tell us? The limit of a product is equal to the product of the separate limits. Okay, does anybody see how I could break up that limit into a product of two limits that would be useful? The x and the, what about the x and the cosine x? Okay, I could do that. But then if I do that, let's just, you can already tell we're going to go a different path, can't you? So if I were to do that, I want to illustrate why though, so this makes sense. I get the limit of sine x times, we'll break it up into two completely separate limits, the limit of 1 over x cosine x. If I try to evaluate those directly, I get 0 times, well, we're going to call it infinity eventually, right? I get 1 over 0, which is undefined, okay? And that ends up with 0 times infinity is itself an indeterminate form. We don't talk about that one very much yet, but that's one of a whole slew of indeterminate forms that we have. The one we mostly focus on now is just 0 over 0. So that doesn't really help us because we still are indeterminate there, okay? Now keep in mind, this is 0 over 0, right? My original limit that I'm working with. When we deal with these trig limits, we don't get to cancel stuff like we did before. Our strategy before was always we'd try to somehow work it out so we could cancel the factors that were causing the indeterminacy and fill in the hole, right? We can't do that here, but what we can do is we could rely on these two limits to resolve the indeterminacy. Does anybody see a part of that that's going to work in a way where when we take the limit, it's no longer going to be 0 over 0? What do you think, Jonathan?
I don't know how I'll do this, but maybe we'll like use one of the special.
We will, yeah, we will. Do you see one of the special limits there? Yeah, it's sine x over x, right? So we could extract that as one function and then have that, we'll look at this as the product of sine x over x and whatever else is being multiplied by that, which would just be 1 over cosine x, right? So we've got these two parts. We could rewrite this limit as the limit of sine x over x as x approaches 0 times the limit of 1 over cosine x as x approaches 0. Okay, what's the answer to the green limit? 1, right? That's given to us. By definition, that's 1. What's the answer to the orange limit? What's cosine of 0? Well, we need that unit circle day big time. Cosine's the x coordinate, right? What's the x coordinate at 0 on the unit circle? It's 1. Yeah. So 1 times 1 is equal to 1. That's the limit. Okay, do you see the strategy there? We're just trying to, we have to break this apart in a way where we can separate out one of the two special limits that we know, and that becomes we have a product of limits, and one of the factors in that product is going to end up being one of our special limits, and then we can get rid of the indeterminacy. Okay, give me thumbs on that. Okay, we need some more practice, obviously. Yeah. Okay, let's try another one. How about one like that? Okay, now I'm going to remind you about something. I'm going to rewrite that special limit in a slightly different way here. Here's our special limit. The limit of sine theta over theta as theta approaches 0 is 1. Theta being the argument of the sine function. I purposely used something different than x. Okay, do we have that right now? Does this correspond to our special limit? Okay, but I can't take the 4 out, right? Because you can't, the 4 is inside the trig function. Taking the 4 out it's not that easy. I've got to end up using, in this case, I'd end up having to use the half angle formula twice. It'd be kind of a mess to do, right? Ah, okay. You see the problem. This doesn't match that pattern. What's our theta in the limit that we're trying to resolve here? Everybody agree? The theta is the 4x. So I don't have sine theta over theta as theta approaches 0, do I? I've got sine theta over something different. But I can always multiply by 1, right? In the form of 4 over 4. So I could write this as the limit of 4 sine 4x over 4x. There's my 4 over 4. And as x approaches 0, wouldn't you agree that 4x also approaches 0? Doesn't that make sense? All right, give me thumbs on that. Does that make sense to you that if x approaches 0, 4x approaches 0? Right? Okay. Multiplying something that's vanishingly small by 4, still vanishingly small, right? So we can arbitrarily, we can do this without any special argument. We can just say, okay, well, we can make that a 4x approaching 0. That's fair, because the two are equivalent statements. And now we're pretty close, right? Look at this. I've got sine theta over theta. As theta approaches 0, I've just got that 4 there. Well, what do I do with the 4? Take it out. And we take it out, and we know we can do that with this property of limits. Scalar multiple property, right? The limit of a constant times a function equals the constant times the limit, right? So in other words, in the language of calculus, kind of the working language of calculus, we would just say, well, let's just, when you're working with your buddies in college on this stuff, you say, oh, we'll just pull that 4 out front. That's how you'd say it, and that's what you do. We're going to take that 4, and we're just going to pull it out in front of the limit. So we end up with 4 times the limit of sine 4x over 4x as 4x goes to 0, which is 4 times, what's that limit equal to? 1. Everybody get that? Okay. Because it follows our pattern. So the answer is 4. Okay, how are we doing? Give me thumbs on that one. Yeah. hmm So in other words, the limit of a constant times a function equals the constant times the limit of the function, right? Okay. Yep. Yep. You can always pull a constant out of a limit. Yep. It's just almost like factoring it out, right? Okay. How about this one? Any clever approaches to this one? Well, yeah, that's the goal, right? Can't do that. Multiplying by 4x over 5x means I'm not multiplying by 1. So if I don't multiply by the multiplicative identity, I'm changing the problem. Can't do that, right? We just want to simplify the problem. If I multiply by 5 over 4, again, I'm going to change the value of that limit because I'm multiplying by something other than 1. You guys are on the right track, though. Okay, you could do that. 5/4 over 5/4 is equal to 1. You could do that. That's fine. That would work. I'm going to suggest here might maybe a slightly easier way to think about this. That works. No. Mm-mm. 5/4 over, if I multiply by 5/4 divided by 5/4, I have multiplied by 1 and by the identity property of multiplication. What's that? Oh, 4/5 over 4/5. That's fine. Yeah. 4/5 over 4/5. There you go. I see what you're saying. Yeah, that's right. Okay, but maybe an easier way to think about it would be to pull that 5 out front, and then we got the same problem we had before. Take your pick, but to me, this seems like this might be a little bit easier. Now I just multiply by 4 over 4. See what I'm saying? Either way, doesn't matter. I have to multiply top and bottom by, well, I mean, the 1/5 is not separate from the limit. It's all part of the same product, right? I have to multiply the numerator of that whole expression by 4 and the denominator by 4. So, I mean, I could put those 4s here. And then pull that 4 out front, right? I would just do that, wouldn't I? Right? So I end up then with, and that, by the way, that's a 4x approaches 0, not 54 out front or 5 times 4. Because it has to match my pattern. Has to match this pattern right here where sine theta over theta as theta approaches 0. See what I'm saying? Okay. But they're interchangeable. So then I end up with 4/5 times the limit sine 4x over 4x as 4x approaches 0, which is just 4/5 times 1, right? Which is 4/5. Okay? Make sense? Okay. All right. How about that one? Can't take a sign out. That's not a constant. It's a sign of a variable, right? So that's a function. Mm-hmm. Well, no, that's that special limit, right? It's indeterminate. It's 0 over 0, but it's equal to 1. Ideas. What do you think? Jonathan, you got an idea?
What if you do like you split both the signs, so you'll say sine 4x over 1, and then you'll have another limit where it says 1 over sine.
Okay, let's start with that. How about? Is that what you're going to say? Okay. Anything else anyone wants to add to that step? Okay, let's do that. So we've got these two. We'll color code this here. We've got these two different limits. We're going to break these apart. So this is equal to, and I'm not going to break them into separate limits yet. And by the way, when you're just doing it, like if you're showing your work on an AP test, you would want to break up, which is what I'm looking for, like this guy. We'd want to break these up into separate actual limits. But if you're just doing work to get an answer on a problem set or something, I mean, really, do you have to break these into separate limits? No, really not. You could just say the limit of sine x over x times 1 over cosine x and just evaluate it that way too, right? Like that's what I wouldn't write the whole. This is a lot of writing to write out two separate limits. To be technically accurate and true, you would have to do that. Whoops, there. Okay, so we're going to write this as the limit of the product of sine 4x times 1 over sine 5x. Now what? Okay. Take it out, you mean? Okay, that's a good idea, right? We need to get, somehow eventually we need to get a 5x with this guy and a 4x with that guy, don't we? For both of these to go to 1. Agreed? So what if we did it this way? What if we said, okay, instead of making it a 5x, what if we just said, let's multiply by x over x? Like right from the beginning, I could have done that, right? See what I'm saying? Okay, and so then this is going to become, what color am I on here? Green. So this is going to become an x there, and this is going to become an x there. Okay, and now it's a pretty good time to break those apart into separate limits because those are both pretty doable limits now, right? We've got it down to a place where we're going to get this thing. Okay, what do I have to do to the green one to resolve that? Multiply by 4 over 4. And we're going to put one of the top 4 we're going to pull out front, bottom 4 goes to the bottom, right? Okay, and I'm going to make that a 4. Okay, what about the orange one? 5 over 5. Which one goes out front, top or bottom? Yeah, right? I'm going to pull out that, factor out that 1/5. So we're going to do a 5x and a 1/5 out front. And we'll let this 5x go to 0, right? So now look, okay, does this make sense up here? If the limit of sine theta over theta as theta goes to 0 is 1, the limit of its reciprocal is also 1, right? Because the reciprocal of 1 is 1, okay? So for that reason then, would you guys agree that this one right here goes to 1 and this guy right here goes to 1, right? And so what do I end up with then? I end up with, here's my 4 out front times 1 times 1/5 times 1. Everybody see that? So I end up with 4/5. Okay. I'd say really the key step on that one, and that's a pretty common type of problem you might see, is just multiplying top and bottom by x, right? So you get it, that way you're going to be able to capture 1x in the numerator and 1 in the denominator, which is part of the pattern that you need. Okay. All right, see if we have time for one more. How we do, was that okay on that one? We good on that? Okay, let's try one more, see if we have time. Okay, yeah, this is a good one. I like this one. Okay. This is a little tougher. Now, that question about the identities rears its ugly head now because the identities are important. This does not match either one of our special trig limits remotely. Okay. But there's a part of this that you could look at and say, aha, there's something I can do with this pretty quickly. What about the bottom there? What do you think? It's not, but it could be made into an identity pretty easily. If I multiply the top and bottom, which is almost always what you do, right? You almost always are multiplying top and bottom by something to algebraically manipulate that expression inside the limit. What could I multiply what do I need to multiply the bottom by to get like the most common trig identity of all time, the Pythagorean trig identity? Remind us real quick. What is that, somebody? What's the Pythagorean trig identity? Oh boy, we better do, I'm going to have to whip out a little because we got to, this is just the one thing we'll do today on the unit circle, right? If we know that this is angle theta, then the coordinates on the unit circle are cosine theta and sine theta, right? Cosine is the x coordinate. Agreed? Okay, it's a unit circle, so the hypotenuse is 1 there. The length of that line is 1. So we could just create a right triangle out of this, couldn't we? Right? If we create this right triangle right here, what do we get? Well, the x coordinate is cosine theta. The y coordinate is sine theta. So now you tell me, what's the Pythagorean trig identity? Well, it's a right triangle. What's Pythagorean theorem? There you go. Yeah, right. Leg squared plus leg squared equals hypotenuse squared, right? So we get sine squared theta plus cosine squared theta equals 1, right? So there's our Pythagorean identity. Right? Okay, so have that up here, but we're pretty darn close to it, right? When we have this Pythagorean identity, it doesn't really do it. It just relates sine squared to cosine squared is what it does, right? What could I do on the bottom? What could I multiply by to get a piece of that? Say it again. Okay, if I square it, the problem is if I square it, I'm going to get cross terms, right? Because a plus b squared gives me a squared plus 2ab plus b squared. I don't want those cross terms. So how do I avoid cross terms? Multiply by you guys have already done this trick once. What do you call it, Olivia?
I don't know what it's called, but he was cosine.
That's it, the conjugate. The conjugate, right? Because, and again, we fall back on this conjugate pattern. The conjugate pattern, maybe you're starting to see a little strategy with this now. Whenever we don't want to get cross terms, we want to only have something squared minus something squared, we fall back on this pattern. Here it's very useful, right? Because in the Pythagorean identity, we don't have any linear terms, right? They're all squared. So if we multiply top and bottom by cosine x plus 1, look what we get. On the top, we get 9x squared times the quantity cosine x plus 1, if we just multiply straight across, right? On the bottom, we get a squared minus b squared. Well, what's that bottom equal to by the Pythagorean trig identity? And what would I have to do here? I'd have to subtract the 1 to this side and subtract the sine squared to that side, right? Negative sine squared. Everybody agree? In one step, I would get cosine squared theta minus 1 equals negative sine squared theta. So there you go. There's a negative sine squared theta. Right? Good. Okay, now we can begin to slice and dice this thing a little bit. Let's see if we can break this apart into a way where we could remove the indeterminacy that we never even checked. But it is, if I try it, it's 0 over 0, isn't it? Okay, so what can I do? How can I break this thing apart? Part that I know the limit. What's the part of that that's going to make this all good? Which special trig limit am I gunning for here? Which is the one that's going to be useful to me, do you think? Okay, sometimes this is helpful. If I try to evaluate this directly, where are my zeros over zeros coming from? I'm getting 9 times 0 times 2 divided by 0, right? That's not a problem. That cosine x plus 1, that's not going to go to 0. What's the part that's causing the indeterminacy here? The sine squared x and that x squared, right? So this is, everybody agree, this is the part right here. That's the part we want to pull out and separate from the rest of it, right? Everybody agree? Okay. When are we out of here like in 1 minute? Well, I'm going to try to do something here. And if I don't finish, we'll finish it tomorrow. So here's what that would look like. Oh, I failed. All right.